Swayam Prabha. Digital India. Educated India.
Welcome to today class of nonlinear vibration. So, in this module we are discussing regarding the applications of nonlinear vibration. In the first 3 classes, so we have discussed regarding the vibration of continuous system, where we have discussed regarding the vibration of a beam subjected to arbitrary base excitation or where a mass is attached at an arbitrary position. So, in the second sets of applications, so we are discussing regarding the nonlinear vibration observer. So, last class we have started this nonlinear vibration observer, and here we have discussed the applications of many applications of nonlinear vibration observer. Also we have discussed regarding how it is different from vibration isolations. So, what are the passive vibration observer, active vibration observer and this hybrid vibration observer. In case of the passive, so we have only spring and damper system attached to the system. So, we know regarding the tuned vibration observer, when this excitation frequency equal to the natural frequency of the secondary system. So, here you can see several pictures of the vibration observer what we have discussed last class. We made some literature review regarding the active, passive and hybrid vibration observer, and so we have started the derivation of nonlinear equation of motion or derivation of equation of motion of different vibration observer. In this vibration observer, we are particularly interested for these piezoelectric stack actuators, and here we have discussed regarding the linear and nonlinear analysis of active nonlinear vibration observer by displacement and acceleration feedback to suppress the vibration of single degree of freedom system, spring mass damper primary system under external harmonic and parametric excitation. Already you know what is harmonic excitation. If the forcing is in the form of sine and cosine, then it is known as harmonic excitation, and in case of the parametrically excited system, you can find a time varying term which is coefficient of the excitation term. So, initially we apply this Laplace transform, or initially we have derived this equation of motion of the system and then apply this Laplace transform to write down the characteristic equation. So, this is the systems we have taken. So, here the primary system has mass m1, secondary system has mass m2. So, the primary system is supported by spring stiffness spring k1 and damper c1, and the primary is connected to the secondary by a spring k2, damper c2 and a piezoelectric stack actuator with stiffness kpe. Also it is connected to the mass 2 by another spring k3. So, we can find the equivalent stiffness of this k3 and kpe, and the force in the stack actuator or the displacement in the stack actuator can be written using delta. So, delta will be equal to n d33v. So, where n is the number of stacks in the stack actuator and V is the voltage applied and D33 is the material property of the actuator material. So, that way we can write down the force applied by the stack actuator and we can derive this equation of motion. So, in this already we have studied this part. So, here we have derived this equation of motion. and in this equation motion particularly, let me repeat. So, you can combine this K3 and KPE to have a equivalent stiffness, which is equal to Kp K3 by Kp plus K3. So, this equation, that is for the, you can draw the free body diagram for the primary system and the secondary system, and applying Newton second law or D'Alembert principle, you can derive this equation of motion. So, now by dividing m1 in the first equation, the equation can be reduced. M1 in the first equation we have divide, and then by taking this k1 root over k1 by m1 equal to k1 by omega, k1 by m1 root over equal to omega 0, and taking a scaling taking a non-dimensional time, tau equal to omega 0 t. The equation can be non-dimensionalized by also taking a non-dimensional displacement parameter x1 equal to x1 by x0 and x2 by x2 by x0 and x equal to x2 minus x1, k equal to kr by k1 and mu equal to m2 by m1, V equal to V by V0, V the voltage applied. So, V0 is the reference voltage you can take, and then omega 0 equal to root over k1 by m1 and omega 2 equal to root over k2 kr by m2, and this external frequency omega 2 equal to omega small omega 2 by omega 0. So, the damping parameter zeta 2 equal to C2 by 2 m2 omega 2 and zeta 1 equal to C1 2 m1 omega 0. So, that way by taking all these parameters, so we can reduce to these two equation. So, here you can see this lambda parameter. So, lambda equal to n d33 V0 by x0. So, this is due to the piezoelectric property of the stack actuator. So, we got this parameter lambda. So, this is the piezoelectric property due to piezoelectric material. So, then in this system, so what we can do? So, we can apply this control force also, we can use a controller. So, we have a primary system, this primary system. So, the output is given to be x1 double dot. So, here we are taking acceleration feedback. So, if we are taking a acceleration feedback, so we have the accelerometer we can put. So, it can sense this acceleration and it will give the acceleration to the controller. So, in the controller, so we can write down this control force. So, you just see in controller we can write down the control force. So, this control force or in terms of voltage can be written V equal to minus Kc x1 double dot. So, this is Kc multiplied by x1 double dot will give you the voltage. So, taking this voltage as the, so taking this as the feedback, now it can be fed to the actuator Ke. So, we can get, so from this Ke into d0, that is the displacement, that will give you the actuator force. So, getting the actuator force, then and this external forcing is Ft. So, it will act on the primary system and we will get the response in this way. So, this control loop, one can draw the block diagram of the control loop and you can study the system. So, here the transfer function, if one write the equation, so as the system is linear, so we can write in using this Laplace transform. So, the transfer function from the primary system, which is the output displacement by the input force, Laplace of input force equal to Fs, and output displacement is x1. So, we write this Gs equal to x1 by xs. So, it can be written in this form, and you can see this denominator contain a fourth order term, that is b4 s fourth, b3 s cube, b2 s square, b plus b1 s plus b0, where this coefficient can be expressed in this following way. So, here this alpha parameter, one can take this alpha parameter equal to k lambda kc, already we have defined k in the previous slide. So, b4 equal to 1 minus alpha. So, actually this to define this b1, b2, b3, b4, we are using this parameter alpha, which is a function of the actuator force, actuator parameters. So, alpha is the function of the actuator parameter like this k, lambda and kc. Kc is the control gain. So, you have seen here V equal to minus Kc into x1 double dot. So, by taking this way this non-dimensional parameter, and so from this characteristic equation, so one can use this Routh-Hurwitz criteria to find the stability of the system. So, it can be shown that the system is stable. So, when this minus mu less than alpha less than 1, mu is the mass ratio parameter. So, if one plot this response, so last class we have seen how we are getting the frequency response and also the variation of the area under the frequency response curve with alpha parameter. So, from this thing one can get the optimal parameter, one can observe these two fixed point, and taking these two fixed point theory. So, one can find the optimum parameter, and from that thing one can find the optimum parameter of zeta or optimum parameter to have the further study. One can take the displacement feedback of the primary system also. So, in case of displacement feedback, so previously we have taken the acceleration feedback, also we can take displacement feedback where this V can be written equal to minus Kc x1, and we can perform the analysis. Similarly, we can find the parameter of alpha for which the system is stable. So, then we can plot these responses also. So, previously we have seen when we are taking the system to be, when the systems are linear. So, we can take the nonlinear system also. So, nonlinear primary system with the displacement feedback also we can take. So, in that case the equation will reduce to this form, and one can use different methods. So, here you just see the nonlinear parameter alpha q x1 q is added to the previous equation. As you know, this superposition theory cannot be applied to this nonlinear system. So, you cannot extend the idea of linear system here to predict the nonlinear response. So, one has to study properly the nonlinear response of the system. So, one can apply method of multiple scale or any other method to study the response of the system. So, here one can take also the spring to be nonlinear in the secondary case. Previously we have taken spring to be nonlinear in the primary case only. So, by taking the spring to be nonlinear in the secondary case, similarly we can derive this equation of motion. So, here this Fc1, that is the control force, can be written equal to Kr into x1 plus delta 0 minus x2, and following the similar way we can have the nonlinear equation of motion. So, after getting this nonlinear equation of motion, so we can further study these equations to find the response. So, here we may apply the method of multiple scales to derive this equation of motion. In this case, you can check the forcing term is of the order of epsilon it is taken. So, here it is epsilon f1. So, if you are taking multiple forces, so in the case we can take multiple forces in the primary system. If multi component of the forces, you just see this is omega 1. So, 3 frequency components are there, omega 1, omega 2, omega 3. So, multi frequency excitation. So, they can be independent, they can dependent also on each other. So, it depends on the user how to set this parameter, or it also depend on the applications where we are taking multiple number of frequencies acting, multiple number of forcing acting having different frequencies. In addition to that, so we have 3 different forcing term, and in addition to that, so we have this control force here. So, control force is also taken of the order of epsilon. So, it is Fc1 into x1 double dot. So, this is the acceleration feedback taken. That way one can find the equation motion. So, now after writing this equation motion, so then one can apply different resonance conditions. For example, one can study the primary resonance condition. So, in case of the primary resonance condition, as we have taken 3 frequency term. So, we can take omega 1 equal to 1 plus epsilon sigma 1 tau 0, and omega 2 also can be taken as 1 plus epsilon 2 plus 1 plus epsilon 2, and omega 3 also can be taken. So, omega 1 can be taken equal to 1 plus epsilon sigma 1. So, this is 1 plus epsilon sigma 2 and 1 plus epsilon sigma 3, where omega r we are taking very away from, that frequency ratio is taken very away from 1. So, here you can see this non-dimensional frequency of the primary system is 1, that is why this omega 1 is taken to be 1 plus epsilon sigma 1. So, if you see this equation, the governing equation, you can see the coefficient of x 1 equal to 1 and m 1 equal to 1, coefficient of the first mass equal to 1. So, when we have non-dimensionalized this thing, the non-dimensional frequency parameter, which is coefficient of x 1 in this case, taking a unit mass, it will be equal to 1. So, that is why we have taken the resonance condition when this external non-dimensional frequency becomes 1. So, in this case the external non-dimensional frequency equal to 1. So, that is why taking this detuning parameter. So, one can write omega 1 equal to 1 plus epsilon sigma 1, omega 2 equal to 1 plus epsilon sigma 2. So, if we are considering, so in case of 3 you just see, in case of 3 it is taken to be 2 plus epsilon sigma 3. So, the third forcing term, if you see, you just check the third forcing term. So, in the third forcing term we can see this is parametric, this is parametrically excited, as the coefficient of x 1 is the time varying term f 3 cos omega 3 t. It will give rise to resonance condition. So, when omega 3 is nearly twice the natural frequency of the system. So, that is why this omega 3 is taken to be twice omega 1. So, omega 1 is taken to be 1. So, that is why omega 3 is taken to be 2 epsilon sigma 3. So, this is the principal parametric resonance condition. So, we are studying then this primary resonance due to all these conditions. So, applying this method of multiple scale, following the similar principle what we have studied before. So, as we have two equations, so it will yield 4 first order differential equation. These differential equations are the reduced equation. So, this a 1 dash, a 1 gamma 1 dash, a 2 dash and a 2 gamma 2 dash equation can be obtained in this way. So, you just see these equations are not simple equation what you have studied in case of the doping oscillator. So, in this case you cannot find the solution or you cannot find a closed form solution like in case of the linear system. So, here you have to, so for steady state this a 1 dash, gamma 1 dash, a 2 dash and gamma 2 dash will be equal to 0 and we will have a set of algebraic and transcendental equation which you can solve to get this a 1, a 2, gamma 1, gamma 2, which will give the response amplitude of the primary and secondary systems and phase of the primary and secondary systems. So, now considering omega r equal to 1 plus epsilon sigma, then we can have this term, that is omega r square minus f c 2 by omega r square minus 1 a 1 e to the power I t 0 equal to 0. Similarly, we will get this equation taking the polar form a 1 equal to half a 1 e to the power I beta 1 and a 2 e to the power I beta 2 and substituting in this autonomous equation. So, we can study the response of the system. So, if we are considering this internal resonance condition, reduced equation will contain the additional term. Taking that additional term, so again we can derive this condition. We have another set of equations. So, now you can see, so in case of the linear system, so we have already observed that if we are considering alpha equal to 0.0001, so this is the response we are getting, frequency response we are getting, and by increasing this control parameter alpha to 0.5 or alpha to 0.99. So, you can see drastically the frequency, the response amplitude decreases, but here one can observe the resonance peak, so is slightly high also, but further increasing this alpha to 0.99. So, you can see the response amplitude is flattened and one can get very less value of response amplitude. For less control parameter, you have seen the response is very high, and by applying this control, so we can easily reduce the response amplitude. So, this part we have seen when we have applied this acceleration feedback, and when you are applying this displacement feedback. So, you see, so we have taken this V equal to minus k c into x double dot, but when we are taking this V equal to minus k c into x 1. So, in that case you can see by applying this control gain. So, it is though it is reducing the response amplitude, but the reduction is not so high as compared to that in acceleration feedback. So, acceleration feedback is giving a better result than the displacement feedback what you have observed here. So, that is in the case of the linear case. So, if we have the nonlinear primary system with a displacement feedback. So, now you can see the bending of the response curve. So, initially q equal to 0. So, this is the response plot similar to that of a linear system, and in case of the nonlinear system it is tilting towards right. So, in this case we can have a broad band of frequency for which the response amplitude is very high. Previously we have a less, so we have a less range of frequency for which we have the response amplitude to be very high, but when the system becomes nonlinear. So, we have a larger frequency range for which the system become nonlinear, or the system response amplitude is very high. By changing different control parameter, we can find or we can observe. So, what will be the response amplitude of the system. So, the response amplitude of the system can be controlled then by passively by controlling those system parameter, or actively by applying this voltage and controlling the piezoelectric material property. So, here you can see, so these are the frequency response for different value of k 11. So, we have taken a subharmonic resonance condition also, subharmonic. So, in case of the subharmonic frequency response curve for primary system. So, this is the subharmonic case. So, the previously we have seen the primary resonance case, and this is the subharmonic resonance case. So, this is also for the subharmonic response. So, when alpha is taken to be 0.99, in this case the response alpha is taken, the control force alpha is taken 0.0001. By taking different k 11 value. So, we can observe how shifting of the frequency response takes place. So, as we are increasing this k 11, so our natural frequency, non-dimensional natural frequency of the system increases. So, that is why there is a shifting of the frequency response towards right. One can plot the time response. It can easily be seen that when alpha equal to 0.0001. So, one has very large amplitude of oscillation and it takes a large time to settle. So, for example, here till 100 also it is not settled, but if we are taking very high value of alpha. So, you can see it settle down very quickly to its final value. By taking proper control parameter and acceleration feedback, here we have shown that the response amplitude can be conveniently controlled in case of the vibration observer, or it can be observed. We have seen the optimum parameter for the observer configuration obtained using fixed point theory. So, from the linear analysis it is found that the amplitude of primary system without active force is 6.45 to the static deflection, but its amplitude reduces to 1.15 times to the static deflection. 82% amplitude is controlled in this case. Similarly, Nonlinear analysis also investigated by considering a cubic nonlinear stiffness along with linear stiffness in the primary system. So, comparing the linear analysis in the nonlinear analysis, the maximum amplitude of the primary system reduces 0.1036 for the primary resonance condition when harmonic force is acting on the primary system. One case of superharmonic response is also studied. So, for the primary system which shows more hardening effect. So, you have seen, so it is tilted towards right. We have observed the hardening effect in the frequency response when less controlling force is applied. So, time response shows the effectiveness of the settling time of the primary system when the observer is used. A nonlinear hybrid vibration observer with quadratic and cubic nonlinearity in primary system also is studied, and here the mass ratio of 0.01 between the observer and primary system is considered for the analysis. So, you can note that the in general literature a mass ratio of 1:20 is considered, but in this case you can see we have taken a mass ratio up to 100 also 0.01, that means. So, m2 by m1 equal to 0.01, that is 1 by 100. So, 100 times. So, we are able to control the vibration of the system by putting a mass 1 by 100 times that of the primary mass. By using this nonlinear analysis, you have seen we can control the vibration or we can observe the vibration of a nonlinear vibration observer by putting a mass 1 by 100 of that of the primary system. So, this is the advantage of using the nonlinear vibration observer. So, let us see another similar problems where we have taken this nonlinear dynamics of this active nonlinear vibration observer with time delay. So, generally when we have applied the control force, so suddenly it will not react and it will take some time to react. That is why there will be some delay in the response. If we are considering that a time delay, so this analysis will be modified. So, in this case we are going to study the response of the system if there is a time delay in this acceleration feedback to suppress the vibration of a single degree of freedom spring mass damper primary system under external multi hard harmonic and parametric excitation. So, previously we have taken weak forcing. So, the forcing term was written epsilon time by using the bookkeeping parameter epsilon, which signifies that we have taken a weak forcing, but in this present case now we will take a hard harmonic excitation. So, that means this excitation term will be of the same order as that of the linear part of the equation of motion, and also we will consider this parametric excitation. The excitation term will take in such way that the time varying forcing term will be the coefficient of the response term, that is x1. So, we have shown the same system. So, here this M1 is the primary system. So, you can take any vibrating system actually and you can represent this using a spring and damper system. So, here the damper and the spring may or may not be linear. So, we may consider a nonlinear spring and nonlinear damping also. So, this nonlinear spring and damping, so it is up to you. So, up to what order you are taking. So, in this case the damping is shown to be quadratic and the spring stiffness is shown to be cubic order. So, by taking this quadratic damping in both the primary system and the secondary system and the stiffness parameter or the forcing due to the spring stiffness up to cubic order, then we can write down this equation of motion. So, after writing this equation of motion, here we can apply control force similar to the previous case. Here the control force is taken equal to, so the control force Fc will be equal to, taking this acceleration feedback, it will be Kc will be equal to Kc into x1 double dot. The equation of motion can be written in this way. So, here delta 0, that is the displacement of the piezoelectric stack actuator, delta 0 equal to N d33 V, like previous case here also we have taken the same way, but this control force here it is written equal to K R into x 1 plus delta 0 minus x 2. So, delta 0 is the displacement of the stack actuator, x 1 is the displacement of the primary system. If we are not considering the stack actuator, then it could have been different. So, now by considering the stack actuator, so we have to add this delta 0. So, total displacement will be x 1 plus delta 0 minus x 2. So, this f c is written equal to k r into x 1 plus delta 0 minus x 2. So, where k r equal to the combined series stiffness of k p e and k 3. We can take this control law in this way. So, now we are taking a time delay feedback. So, taking tau d as the time delay. So, we can write V equal to K C into x 1 double dot t minus tau d. So, here you just see here we have taken this time delay as tau d. So, in this acceleration feedback, so we are assuming there is a delay of tau d. So, when you are applying the response, when we are applying or sensing the response, and there will be a time lag when it will actually actuate. So, for the actuation, so we can take V equal to K C into x 1 double dot into t minus tau d. By taking this way, so we can write down this equation of motion in its non-dimensional form. This control force now can be written F c equal to K R into x 1 minus x 2 plus n d 33 K C into x 1 double dot into t minus tau d. The governing equation of motion can be written in this form. So, that is taking this tau 1 equal to omega 1 into t, omega 1 into t we have taken in this case. So, as we have taken this is equal to omega 1 into t. So, you can write down this equation in this form d square x 1 by d tau square plus omega n 1 square x 1 plus 2 zeta 1 plus omega r by mu 2 zeta 2 d x 1 by d tau equal to omega r square by mu into x 2 plus 2 zeta 2 omega r d x 2 by mu 2 zeta 2 omega r by mu into d x 2 by d tau and minus alpha 1 to x 1 square. So, this is the quadratic nonlinearity we have taken, and alpha 1 3 cubic nonlinearity is taken, and then this is due to the difference in that alpha 2 1 x 1 minus x 2 whole square. Similarly, cubic order nonlinearity alpha 2 3 x 1 minus x 2 whole cube plus this forcing we have taken, 3 different type of forcing we have taken. So, 2 forcing, that is F 1 cos omega 1 tau plus F 2 cos omega 2 tau. So, plus, so this is the parametric forcing term, this is F 3 cos omega 3 tau, which is coefficient of x 1. So, minus F c 1 d square x 1 tau minus tau d by d tau square. So, here you just see this forcing are not taken of the order of epsilon. So, in that case we can tell that is to be hard excitation. Similarly, we can write down this equation for x 2. After writing this equation for x 1 and x 2, we can non-dimensionalize that thing. So, by dividing this m 1 and then writing, you just see this omega r is taken to be omega 2 by omega 1 and omega 2 equal to k 2 plus k r by m 2 root over, and omega 1 equal to root over k 1 plus k 2 plus k r by m 1, and this mu equal to m 1 by m 2, 2 zeta 2 equal to c 2 by m 2 omega 2, alpha 1 2 equal to k 1 2 by m 1 omega 1 square. Similarly, alpha 1 3 equal to k 1 3 by m 1 omega 1 square, alpha 2 2 1 equal to k 2 1 by m 2 omega 2 square, alpha 2 3 equal to k 2 3 by m 2 omega 2 square, and these forcing term are non-dimensionalized as f 1 by omega 1 square x 0, f 2 by omega 1 square x 0 and f 3 by omega 1 square x 0. Similarly, f c 1 equal to written k c Kr Kc Nd33 by m1, where omega 1 non-dimensional first frequency equal to omega 1 by omega 1, omega 2 equal to omega 2 1 by omega 1, and omega 3 equal to omega 3 1 by omega 1. So, you can note that the equations what we have written is not unique. So, you can write the equation in a different form. Also, you can write the linear part using this matrix form, and you can then apply this modal analysis method to reduce this mass matrix and stiffness matrix to the uncoupled form, and then one can write down this equation separately. So, where the linear part will be uncoupled and the nonlinear part and some forcing part may be coupled. So, that will give or that will yield another set of equations. You may also use this weighted modal matrix. So, instead of this modal matrix P, one can use this weighted modal matrix. So, in that case the resulting mass matrix will have the unit vector. So, I will be equal to, so I will be equal to identity matrix, and this coefficient of this x, that is the displacement, will contain the eigenvalues of the system. So, it may be omega 1 square 0 0 omega 2 square. So, that way also one can write another set of equations. The writing of this equation is not unique. So, you should understand that the writing of these equations are not unique, but you can reconvert these equations to its original form after finding the response of the system. One can use this modal analysis method to rewrite these equations also. Actually, depending on the applications, you can choose or you can check what will be the order of this damping. So, for example, in this particular case this order of damping are taken to be epsilon order. So, then this alpha 1 2, alpha 1 3, alpha 2 1, alpha 2 3, Fc 1. So, these are taken to be order of epsilon square, and F1 F2 order of epsilon, and F1 F2 F3 are taken to be order of epsilon. In this way, so you can non-dimensionalize and write down the equation of motion by ordering it with the use of different bookkeeping parameter. So, epsilon, so it may be of the order of epsilon, it may be some terms may be of the order of epsilon square, and some of them may be of the order of epsilon to the power 0, epsilon to the power 1, and epsilon to the power 2. So, you may go higher order also, but if you go for higher order, then the number of equations will go on increasing without much increase in the precision value of the response. So, up to second order you may go. So, if you are going for higher order, so you may go for the symbolic software tools or use the symbolic software tools to write down the equation of motion or find the equation of motion. We can get a final set of equation of motion, non-dimensional set of equation of motion. So, where it is written as d square x1 by d tau square plus omega n square x1. So, here you just see omega n1 is not taken to be 1. So, one may take that thing equal to 1. So, if this omega 1 is taken to be equal to omega n1. So, depending on how we are taking this non-dimensional parameter, the coefficients of our equation will change. So, here we have these three forcing, that is epsilon f1 cos omega 1 tau, epsilon f2 cos omega 2 tau, epsilon x1 f3 cos omega 3 tau minus epsilon square fc1 d square x1 tau minus tau d by d tau square. So, here in the forcing, so we have used the acceleration feedback. So, time delay acceleration feedback is taken here. So, similarly the second equation can be written using the time delay acceleration feedback. So, d square x1 is a function of tau and tau d is the time delay function. So, then one can solve this equation by using this method of multiple scale. So, it can be taken x1 equal to x10 plus epsilon x11 plus epsilon square x12, and you just see how the delay term is written. So, delay term is written simply by using the same expression of this one. So, where this tau is replaced by tau 0 minus tau d and this tau 1 is replaced by tau 1 minus epsilon tau d, tau 0, tau 1, tau 2. So, they are of the different time scale. So, here for the delay, so these time scales also has to be modified. So, for example, this tau 0 will be tau 0 minus tau d, tau 1 which is epsilon tau 0, it can be written tau 1 minus epsilon tau d. Similarly, the higher order terms also can also be written this x 1 tau minus tau d. So, that is a delay. By using the delay term, one can write this displacement x 1 in this form. Similarly, displacement x 2 can be written x 2 0 tau 0 tau 1 plus epsilon x 2 1 tau 0 tau 1 epsilon square x 2 2 tau 0 tau 1, and the corresponding time delay term also can be written. So, by taking these primary, principal parametric and 1:1 internal resonance condition. So, here if we are taking omega 2 equal to omega 1, that is the frequency of the first mode equal to the frequency of the second mode. So, in that case we can write this equation in this form by using this detuning parameter. So, you can write omega 1 equal to omega n 1 plus epsilon sigma 1, omega 2 equal to omega n 2 plus epsilon sigma 2, and omega 3 equal to 2 omega n 1 plus epsilon sigma 3. Now, following the previous procedures for internal resonance condition. So, we can take this omega r equal to omega n 1 plus epsilon sigma. Now, we can write the reduced or we can write the terms which give rise to secular term. So, this is the term which gives rise to secular term. So, this term has to be eliminated to get the response of the system. So, here we can take this d a 1 by d tau equal to epsilon d 1 a 1 plus epsilon square d 2 a 1. So, similarly, d b 1 by d tau equal to epsilon d 1 b 1 plus epsilon square d 2 b 1. Finally, we can get a set of reduced equations, and those reduced equation can be solved to find the response. One can use non-autonomous form. So, previously we have taken in terms of, so you just see a equal to half a, capital A equal to half a e to the power I beta generally we take, and then we can convert that beta to gamma form or to remove the time terms in this equation motion to make the equation autonomous. So, we can use that one. So, we have to use this gamma 1 equal to sigma 1 t 1 minus beta 1, gamma 2 equal to beta 2 plus sigma minus sigma 1 into tau 1. By properly writing these terms, we can make the equations autonomous. Here these time terms will be eliminated in the steady state. So, one can use this method of multiple scale version 1 or version 2. So, in version 2, so the normal way when we are deriving, that is version 1. So, in case of the version 2, the term d 1 a 1, d 1 square a 1, d 1 b, d 1 square b 1 present in the equation with order epsilon square are made 0, whereas in MMS version 1 these terms are kept which is derived in the above equation. Hence, method of multiple scale version 1 contains some additional term. The secular term and the solution obtained using those equations are modified. So, if you want to use method of multiple scale version 2 proposed by Rahman and Button, so you can write down these equations in this form. So, here the term with d 1 a 1, d 1 square a 1 and then d 1 b 1, d 1 square b 1 are eliminated while studying the terms, which gives rise to secular term. So, these are the equation we obtained. Now, solving these equations. So, you just see we have a set of equations. So, we can solve these equations by using numerical method, particularly you can use this Newton's method, which actually required the initial condition to find the response of the system. So, here to find this initial condition, you may solve this equation by using ODE for 5 or by using this Runge-Kutta method, and then taking those response as the initial condition, one can make further study to find the response of the system. Otherwise, one can use this continuation technique to find the response of the system for a wide range of frequency. We have studied the how we can use this controlling force, and in this numerical analysis we will see by taking a harmonic force of F1 equal to 0.1. Here you just see we have taken this omega equal to 1. So, that is why that omega is the coefficient of x1 to be 1. So, that is why to make the forcing term to be weak forcing or hard forcing. So, depending on that thing. So, we have to choose this F1 and F3. So, here F1 is taken to be 0.1 and F3 equal to 0.01. So, mass ratio of the primary system to observer is taken. So, already I told you that it is taken to be 100. Previous literature limit their analysis up to mass ratio of 20. So, damping parameter of the mass and observer is taken to be 0.002 and 0.004. So, the stiffness at the junction of PZT actuator and the observer of mass Kc is varied from 0.001 to 0.1. So, quadratic and cubic nonlinearity stiffness are considered to be 3% and 4% of the linear stiffness of the primary and of the primary system and the observer respectively. So, controlling force Fc1 is varied from 0 to 0.002. So, taking these numerical values, so one can study the response of the system. So, here the response of the system. So, initially we have plotted the time response. So, clearly you can see the time response without control and with control. So, with control, so the line you can see clearly it shows that it required very less time to control the response of the system with a control force, but without control force it will take a very large time to obtain the steady state response. So, in the first figure you have seen this Fc1 equal to 0 and Fc2 you can take to be 0.002. Similarly, in the primary system Fc1 equal to 0. So, in the first case, so in this first figure we have taken Fc1 equal to 0. So, which is without control force, and Fc1 by applying a very small Fc1, that is control force equal to 0.002. So, we can see the settling time is very less. So, quickly it reduces to its equilibrium position by applying this control force. So, similarly, primary system observer with Fc1 equal to 0.002. So, the first case it is Fc1 equal to 0.002 and alpha to C equal to 0.001. Here the primary system and observer are shown. This is the primary system response. You can observe that primary system, this is the primary system response and this is the observer response. So, the primary response is reduced significantly, but the observer response increases. In case of the vibration observer, so that takes place. So, generally we control the vibration of the primary system and the secondary system oscillate, and to control that oscillation of the secondary system. So, generally, so damping is used in the system. The system can be made nonlinear or the damping can also be used. In the third figure it can be clearly shown the displacement and the time. So, primary system. So, this is the primary system and this is the observer. So, now by taking this time delay, so time response of FC1, so this is the time response of FC1. So, primary system with time delay, so this is primary system and observer with time delay, primary system with no time delay. So, here in this case there is no time delay in the primary system, in C primary system with no time delay, observer with no delay. So, it is without delay and first two figures are with delay. You can easily see with delay. So, we can control, actually here you can observe some beating type of phenomena also in case of the systems without delay, and here with delay you can easily see the response amplitude is reduced, the response amplitude is reduced. So, the delay is acting. So, we have observed that the delay is acting as a damper to the system. Using this nonlinear analysis, using method of multiple scale, if you find the response, it is showing this hardening type of effect with the different bifurcations. So, you just see here we have this half bifurcation and here we have the saddle node bifurcation. So, these are the different responses we have observed in this case. So, in the present work, so we have seen this hybrid vibration observer with the displacement and acceleration feedback for both linear and nonlinear analysis. When the mass ratio is taken to be of the order of 0.05, that is the conventional work, that is up to 20. We have gone also here mass ratio up to 100 and we have seen the response of the system for different mass ratio and different thing. So, if we can consider the, so now also we can consider other different system, that is subharmonic and superharmonic resonance condition. So, in subharmonic and superharmonic resonance conditions, so we can see the response. One can follow the similar procedure to find the solution. So, in case of superharmonic resonance condition, so you just see the forcing term, the frequency can be taken in a different way. So, this omega 1 can be taken as omega n1 by 3 plus epsilon sigma 1 and omega 2 is taken to be 3 times omega n1. In case of superharmonic, so this is the condition in the superharmonic, that is omega 1 equal to omega n1 by 3, and subharmonic, this is the condition for subharmonic, that is omega 2 equal to 3 into omega n1 plus epsilon sigma 2, and it is parametric also, principal parametric omega 3 equal to 3 to omega 1 plus epsilon sigma 3. Internal resonance conditions also one can consider. So, in that case omega r is considered to be omega n1 plus epsilon sigma 1 and proceeding in the similar way. So, we can get the reduced equation, and after solving these reduced equation we can study the response amplitude. So, here you can see several response amplitudes have been plotted. So, you can observe that the non-dimensional amplitude of the primary system is found to be maximum of 2 with an applied controlling force equal to 0.4. So, without the controlling force the system shows better vibration suppression with a range of 0.02, but only at the resonating frequency, outside the frequency of operation the vibration of the system increases. Also increasing the controlling force to 1.4 produces more vibration in the system. So, the effect of controlling force in reducing the amplitude of the primary system and the observer for the simultaneous primary resonance, principal parametric and 1:1 internal resonance condition is better when the frequency of operation is varied for sigma 1 in the range of 1.6 to 3.4 or at resonant frequency of operation. By controlling this detuning parameter, so in this case we have seen, so we have applied 3 conditions simultaneously. So, we have the superharmonic, subharmonic, as we have taken 3 frequency terms. So, we can apply subharmonic, superharmonic and principal parametric resonance conditions simultaneously. if we are taking only single frequency, then this is not possible. One can do this further analysis. So, there are several other analysis one can do. So, for example, omega j equal to omega 1 one can take, this is primary resonance conditions one can take. Then in this case subharmonic omega 2 equal to 3 omega 1, superharmonic 3 omega 1 equal to omega 1 can be taken, and then principal parametric resonance condition omega 3 equal to 2 omega 1, and internal resonance conditions omega 2 equal to m omega 1, omega 1 equal to m omega 2. Many different conditions can be taken. So, one can take these 3:1 internal resonance conditions also. So, by taking all these internal resonance conditions and external resonance condition, so one can study this observer, and by studying this observer, so one can find the results and one can seize the different frequency response and time response of the system. And in this way, so one can study the nonlinear vibration observer. Also one can study the nonlinear vibration observer by using in this harmonic balance method. Just let me briefly show how harmonic balance method can be used in this way. In this case, you can have the same equation motion, but you can consider this u 1 tau equal to a tau cos omega tau plus psi 1 tau, u 1 tau minus tau d equal to a tau d cos omega tau minus tau d plus psi 1 tau minus tau d, u 2 tau equal to b tau cos omega tau plus psi 2 tau. So, here this a b what we have considered are not constant, but slowly varying function of time. In the previous harmonic balance method, so we have taken these are constant, but here by taking these terms as slowly varying function of time. So, one can initially one can get this a, b and psi 1 psi 2, and by perturbing that thing. So, one can study the stability simultaneously to find the response plot. So, here by substituting this way one can get by collecting the coefficient of sin omega t and cos omega t. So, these equations can be obtained, and from this thing one can get this a 1 dot, b 1 dot, psi 1 dot, psi 2 dot. So, for steady state, so this will be equal to 0, and to study the stability, so one can find the eigenvalue of the Jacobian matrix, and we can study like similar to that of the that we have studied in case of the method of multiple scale. In this way, so one can study the vibration observer. So, whether it is a linear vibration observer, nonlinear vibration observer, it is subjected to single frequency, multi frequency, with time delay, without time delay, with internal resonance condition, without internal resonance condition, and also with 1:1 internal resonance condition, with 1:3 internal resonance condition. So, several different combinations are possible. So, one can use required vibration observer depending on the application of the system. Next class we are going to see one more application. So, to a different system. So, there we can take cutting tool vibration. So, particularly we can take a lathe machine vibration, vibration of the tool and workpiece during turning, and we will use a different method to solve the nonlinear governing equation to obtain the instability region. Thank you.